So my talk, this talk will be on geodesic transcranial electrical neuromodulation, or GTEN for short. This follows actually quite nicely on some of the ideas that we covered in dense rate EEG, because the principles of GTEN builds on the principle of dense rate EEG and source estimation. Okay. So here's the talk outline. I'll do a very brief introduction to transcranial electrical modulation. So just an introduction. You'll hear more, a little more about that later today. And then we'll go into issues in the current research using TDCS, or transcranial direct current stimulation. And then I'll show you how we use GTEN and a pulse protocol of GTEN to change cortical excitability. And then briefly, very briefly, in one slide, show how we then also use GTEN for the treatment of epilepsy. Okay, so just with a show of hands, who's familiar with TDCS, transcranial direct current stimulation? Anybody? Okay. Okay. 4. Have you guys done research with TDCS? Okay. All right. So these are the common names that you'll see in the literature. TDCS. So they're all transcranial, meaning that you apply current at the scalp, and transcranial means through the cranium, or through the skull. And you can use direct current, alternating current, or TACS, oscillatory direct current, random noise current stimulation, or pulse direct current stimulation. Okay? I'll be talking about the pulse current stimulation in our studies. So transcranial current stimulation involves the placement of big patch electrodes in 2 different locations. And you pass current through these 2 electrodes. And as current flows through the head, the current distribution builds up at some site in the cortex. And it's the concentration of the current at these cortical sites that then change the excitability, either makes it more excitable or less excitable. But this is a little bit advanced. Most people don't do this part. They just place an electrode somewhere, assuming that the current will go to the area that they placed the electrode over. Okay? So in one sense, it's a blind way of doing things. It's sort of like the old way of doing EEG or ERP research. You see a component, an ERP component over an area, and you say, oh, it's coming from the area right beneath it. We know that's not true because current flows everywhere, and you can't predict it unless you have a very good model. And remember, I showed this picture in the current in EEG to illustrate that you have these cells that are aligned this way, and that generates the EEG signal. It has to be aligned. The same principle holds for TDCS, or current stimulation. That current has to go along the axis of these cells. And I'll explain that in a minute. So this is the high level, the macroscopic level of if you place an electrode here and you pass current through and you measure the voltage distribution at the cortical surface, it will have some distribution, okay? But if we look at a smaller level, like that cortical patch I showed you, we just cut it and we put it in a bath, and we have an electrode at the top of the cortex and at the bottom of the cortex, and we pass current through, DC current going from positive to negative. Then, and a cell here will experience current flow in that direction, positive at the top and negative at the bottom. Now we can look at a single cell, a single pyramidal cell, and if we pass current through this way, what you'll see is, remember the ions going back and forth, that generates electrical activity that we record at the scalp as EEG. If you pass current through this way, the cells, so current positive going to negative, at the very top will hyperpolarize, meaning that relative to the resting membrane potential, it will be exaggerated, it will be more polarized. But at the very ends here, it will become depolarized. More current, the membrane potential will be closer to firing rate. Now, if you go past current this way, it will have very little effect, because all of this stuff here will essentially the net effect is zero. It has to go along the axis. So in the same principle that we have for generating EEG being radial, it has to be very similar to change neuronal excitability. Yes?
I was confused. You say that the upper layer 5.
Yeah.
So the upper is deeper layer?
Well, in this case, when I say upper here is relative to this figure. So if this comes from a hippocampal slice model, so that when it's sort of inverted.
Oh, I see.
Yeah.
Okay.
Yeah.
Inverted. Then the direction is scalp.
Yeah,
And
that's right.
the opposite is hippocampal.
Yeah. So, well, no, this is this study was done using hippocampal slices, and so the orientation, yes, in normal orientation, layer 5 would be at the lower, but don't mind the layers per se. The layer is not important. What's important is each component, the field, the electrical field relative to this, because you can reverse it. If the current goes from positive to negative this way, this will be hyperpolarized, and this will be depolarized. So the layer doesn't matter. It's the direction of the current flow relative to the...
In usual our scalp,
Yeah.
the neuron,
Mm-hmm.
the action is the scalp, or the dendrite is the scalp.
Is in the upper layers. The dendrites in the upper layer 1 and 2.
The dendrite is the upper layer.
Yeah.
And which is plus? Dendrite is plus or axon is plus?
It doesn't matter. What matters is the direction of current flow. So let's just say this is a normal cortex, and this is the upper layers.
Upper layer.
Yeah.
Upper layer is
1,
dendrite.
2. So 1, 2, 3, 4, 5. If you pass current this way, from positive to negative, it will be the upper layers. The layer 1, 2, and 3 will be hyperpolarized, and the lower will be depolarized. But if you pass current positive to negative this way, the upper layers will be depolarized, and the lower layers will be hyperpolarized. So it's the current direction. If current goes this way or current goes that way.
And you mean the current direction, which is where you place the patches?
Well, so you can place the patch anywhere. So for example, here, this is an electrode, and this is an electrode. In this case, you make current flow from here to here. You can reverse the current and make it flow from here to here. Yeah.
So it doesn't really matter about the direction of the neurons. You can just, depending on the location of the electrode,
Yes, that's
you can
exactly it.
it.
And we'll talk about that in just a minute. Okay. So that's the general idea, or the model from single cell studies. So, in humans, so transcranial electrical or TDCS or TACS, the transcranial part makes it supposedly non-invasive. Okay, so if it's non-invasive, how do we measure changes? How do we know that current is changing brain activity? So this is the typical way of studying the changes. So the first studies, the first modern studies, because actually it's been known for a very long time that current does change electrical activity. You know, back hundreds of years, current changed activity of the brain. Hundreds of years. Back in the 40s and 50s, 1940, 1950s, there were a lot of studies in Russia as well that show that. But it's only within about 17 years ago that it was essentially rediscovered. And it was rediscovered using this paradigm. So you have transcranial magnetic stimulation. Who here is familiar with TMS? Okay. So TMS essentially is this device here. So this is a TMS coil, and you pass current through these coils. And as we know, if there's a current field, there is also a perpendicular magnetic field. Okay, and if that magnetic field changes, then it can induce current flow in a conductive medium. And so this induces current flow. So and then it generates a magnetic field. That magnetic field, if you have it right up next to the brain, will induce current flow in the cells underneath. Okay, and if it's of a high enough magnitude, then you can make the cell fire. Okay, and if you put it over the motor cortex and you trigger the TMS, then it can make your finger move, it can make your limb move, and so on. So that's the idea behind TMS. So if you place it over, remember that hand knob region, then you can make the finger move. Okay, and so you place an electrode around your fingers, and then you stimulate the brain, and then record the amplitude of that movement of the EMG. Okay. And so if you set the TMS coil to a certain power level, and you keep it constant, and then you stimulate many times, and then you get an average of this amplitude movement. Okay? You use that to establish a baseline. So let's just say 80% of the maximum power of the TMS produces 1 millivolt of movement as measured. That's your baseline. Okay? And then you apply an electrode over this area and over the frontal lobe, the opposite side, and you pass current through for some amount of time. So usually between 7 to 20 minutes. Okay? And the subject does nothing. The subject just sits there. And then you turn it off. And then you apply TMS one more time at 80%. And then you watch if this increase or decrease. Okay? And then you do it, you measure it for up to a couple hours and see how that changes. Okay? So you have a baseline, you have your TDCS, and then you measure the muscle activity and compare it to your baseline to see if it changed or not. That's how you measure, that's how they measure cortical excitability. Okay, does that make sense? Okay.
Why you write the TMS during baseline session?
Yeah.
There's no apply any current.
That's right. There is no applied current. Yep.
But
you only apply current here.
Why you write the TMS in baseline session?
Well, that's how you measure the baseline. You use the TMS to establish a baseline of this finger movement.
TMS?
So you apply TMS and then you measure how big this moves. And then you don't do it anymore, you apply current, and then you turn that off, and then you basically do the baseline measurement again. But now, because it's happened after this, you want to measure, you want to compare that to this. Okay? So now this goes to your question of the current flow. So if they applied an electrode here and here, and they make current go from here to here, this is called anodal, or the positive side. Okay? And then you can switch it. You can apply current from here to here. Then this is the cathodal. Now this is negative. Okay? So they run those studies. They first run positive and then positive. And then sometimes they don't do anything. They use a sham. It's like a placebo. Okay? And then they measure, remember, this period, the TMS, and compare it to this period. Okay, so immediately when you turn off the TDCS, you do your TMS. Okay, so this is time 0 is immediately after you turn off the TDCS. Okay, and then you'll see over time, 5 minutes, 10 minutes, 15, up to 60 minutes later, if current is positive over here going in, your motor response gets bigger compared to the baseline. So this is baseline here. 0 is baseline. So this is a percent increase over baseline. So it gets stronger, given the same amount of TMS power. Okay? If you apply negative current or positive current here and negative here, then the EMG gets smaller. Okay? And if it's a placebo or sham where you don't apply any current but let people think that you're applying current, nothing happens. Okay? So this is why they said, and this is the typical response. Okay? This is an average response across people. All right. And this is how they conclude that if you apply cathodal, then you have a decrease in activity. If you apply anodal, you have an increase in excitability. Okay? But this is a net sum effect, meaning it has no consideration for the layers. It's just a sum that you measure here. Okay? And so that's a little bit different, of course, than the cellular model where you have excitability changes across the axis of the neuron. Okay? Just keep that in mind. But this, if you go into the literature, this is the common understanding as we know it today. This is what everybody believes, okay? The problem is this. If this is the average, okay? But if you look at each person, if you ran a study of 30 subjects, let's just for example, not every subject responds that way. Okay? This is the typical response. Only 36% of your subject will respond that way. 38% will have a facilitatory effect, no matter if it's positive or negative. It's facilitatory. 5% will be inhibitory. It doesn't matter which direction, it will be inhibitory. And then 21% will have the opposite effect. So this is a real problem, right? Because if you, let's just say if you use TDCS to change cognitive mechanisms, or if you want to use TDCS for treatment, and you want to, for example, which we'll talk about a little later, in epilepsy, it's an excitability problem. And so you want to decrease excitability. You want to make it inhibitory. But if you can't predict what's going to happen, you can't use it. Okay? So this is a real problem. So why is that? Why is it why is there so much variability? Well, these are some possible explanations. Maybe there are just individual response variability, and some of it is uncontrollable, meaning that it's very similar to taking medication. Yeah, some people don't respond, others do, and we don't know what those reasons are. It's just variability that we can't control. Maybe it's because there are controllable variability, meaning things that we can control but we don't at the moment. The first is the individual anatomy. Remember when I said you place an electrode here and you think that you're hitting that area, but current can flow anywhere. And if you don't know, you don't know. And maybe that's the reason why it's so different for everybody. The other is dosing. Just because you say you pass 1 milliamp of current through, doesn't mean that when it hits that hand area, it's the same amount of current for everybody. You just don't know. But you can control all these things. Right now, nobody knows. Okay? So maybe that's a reason. The other is it the current that we apply, like DC current, while we can do that, is it a physiologically reasonable thing to do? Is that the best way to change the way current to change neuronal activity? Because we don't really have natural DC activity. There is, but it's a very limited sort of phenomenon in neuronal functioning. People think there are DC states, but is that because we know a lot of EEG is oscillatory-like, okay? And actually, there are other parameters that I don't list here, and I won't go into at all. But these are not the only. These are just some possible explanations, okay? So then we go to the question of what is GTEN? What do we mean when we talk about GTEN? What's unique about GTEN? So certainly, this is the traditional, yeah? You have this big patch electrode, and if you pass current through, if you have a good model, you can try to determine where current is maximum. With GTEN, certainly we can replicate that, meaning these are the EEG sensor nets, these nets here. We can pass current through each electrode, and we can replicate this. And we can model that they're about the same, okay? But that's not what's unique about GTEN. What's unique about GTEN is this. Remember in my previous presentation, I talked about the high-resolution head models that we build for source analysis. That's really what's unique about GTEN, and it's unique in this way. And I'll talk about it again. For every single individual, we can create a very high-resolution model of the head. So here is a MR. We segment all these tissues that I talked about before, and we can predict current flow from the inside out. Yeah, and that's how we do our source analysis. We predict current flow. So here's the model of the brain, and each one of these dots or each one of these color patches is a dipole. We say, all right, current, if it starts here, it'll flow out somewhere, and then see at the scalp as a EEG signal at certain sensors. And we model all the conductivity properties of the tissues, like air, white matter, gray matter, CSF, skull, scalp, eyeballs. That is the secret, okay? That's the secret to GTEN. And so how do we know that our model is good, right? One way, of course, is to do the source analysis that we've done, okay? But that's still maybe is not as convincing that we have a good model. Another way that we can verify that our model is good is we can predict how current should flow and compare it to the real world. Okay? So the real world situation is this. So if we take these 6 electrodes, we apply the net to my head, and then we inject current, we pass current through. Yeah? Current goes from these 3 electrodes to these 3 electrodes. Okay? We don't care what happens inside the head. So, and then when we pass current from here to here, then we measure the voltages at all of these other sensors. Okay? And then we plot it, the voltage. Okay? So here's channel 1 through, let's just say, 256. Okay? And then we inject current through these, and then we measure the voltage at all these other ones. And that's the real data is red. We plot it. In our high resolution head model that we build, we can predict if we injected current through these electrodes and we measured it in our model at all these other, how does it compare through to the real world? Okay? So you can see here when we do that, the data, which is red, matches up very well with green. The only way that it can match up well is that all of the other parameters, all of the current flow through the inside has to be accurate, because current goes in and it comes out everywhere. So it goes through the scalp, it goes through, So to the extent that it matches up, we know our head model is good. If our head model is not good, this data will not match up. Okay? So that's another way of validating the data or verifying. So once we have that, we have this idea, or we can use what's known as the reciprocity principle. And this has been known for a long time, which is this. Okay? The reciprocity principle states, if this is a circuit, and we have a current source here, and we have resistors through this circuit, and we measure the voltage, if we pass current through, we measure the voltage here. If we switch this for the current to go from here, and we measure the voltage here, it will go through the same thing. That's reciprocity. The brain, or the head, you can think of it as just a circuit like this. Each tissue is one of these resistors. Okay? So if we pass current through, if this is the inside of the head, and where the neurons are, they generate current when they're active, and we measure it as the EEG, let's just say now we want to target this brain region. How do we target it? Well, the same electrodes that measure that, we pass current through. It has to go back in the same way it comes back out. Okay? That's the reciprocity principle. If you know how the circuit is, it doesn't matter if current's coming from the outside or current's coming from the inside. It'll take all the same circuits. What does that mean in principle? Okay? So in principle, if we compute the potential topography of a source at the cortical surface, we can predict the modulation of the cortex given the sources at the scalp. So if let's just say you want to target this area, the hand region. Because we already have a model that if we turn on this area, it will look like this. It will have blue here and red here. We can use that same topography. All we have to do is know the topography. And then we use that topography to tell us which electrodes to pass current back in. Okay, that's the idea. So how does that work for us to help us deal with this problem of variability. Okay, remember I said there's a lot of variability. And maybe one of the reasons is that everybody, so in their study, every single person gets an electrode put here and an electrode put here. Okay, 30 subjects, same electrode. Maybe that's a reason why we get all this variability. So, but we know that can't be true, right? Because everybody's anatomy is different. So in this study, we try to use, we use the reciprocity principle. We build a high-resolution head model for every single subject. And then we use reciprocity to select the electrodes that we should use for current injection. Okay? And then we also use a pulse protocol. The pulse protocol is well known, right, in TMS. It's the rate. You know, if you have a slow rate or a fast rate, is the rate that determines whether something excitable or not. And there's a good physiological reason for that, which I won't go into, but I can if you have a question. But for now, just know that is the pulse, is the rate of the stimulation that seems to be important to excitability or reduce excitability or inhibition. Okay, so we put those two things together. Okay, so our goal was to induce long-term depression. Okay, regardless of current direction. We're saying it's not the positive or the negative that's important. Okay, number one is the rate, because we know this from animal studies, and we also know it from TMS studies. So it's not the positive or negative that is important. Okay, and our goal is to minimize response variability. And our hypotheses are as follows. Low-frequency pulses will produce consistent inhibitory responses regardless of current direction. We'll see more consistent responses across participants. And because we're using a pulse, very brief pulses, the total charge required to change cortical excitability will be very little compared to previous TDCS studies, because in TDCS you turn it on and you keep it on for a long period of time. So that's a lot of current. We're saying we don't need all that current. Okay? So pulse electrical neuromodulation. This is TDCS. You turn the current on, you keep it on for some amount of time. In pulse neuromodulation, you turn it on and you turn it off, turn it on, turn it off. And you can make it very brief, and then this is fast stimulation, this is slow stimulation. And this is what I mean by, I won't go into it, but the LTD and LTP, long-term depression, which is inhibition, long-term potentiation, which is excitation, really depends on the rate. And the rate influences calcium, how calcium goes into the cell. And that's what changes, okay? That's just very brief. All right. So this is our paradigm. We use exactly the same net, okay? And then we put a little bit of lidocaine. It's just a local anesthetic, you know, so that they don't feel the current. Because when you use TDCS or something, or anything DC, people start feeling it, okay? And then they know if you're passing current or not. And sometimes it can hurt if you use a lot of current. So by using lidocaine, we get rid of all that problem. And then we only use 8 pairs, so 16 electrodes for this study. In concept, you can use up to 80. That's how many current sources we have. And then we use a half a hertz frequency for stimulation. And the pulses are only 100 milliseconds long. So every 2 seconds, they have a very brief 100 millisecond pulse. Okay? And then the injection pattern is different for everybody. And how we determine that is through reciprocity. And I'll go into that. We use the exact same paradigm as I showed. Okay, TMS. Then we use the not TDCS but the pulse for what was it? I forget how long. I believe 17 minutes. Yeah, 17 minutes. So so here we apply for 17 minutes, and then we measure again the responses after. So we apply TMS. Okay. So this is how we use reciprocity. Okay. For every single subject, we use first the TMS to find their maximum response. So we know where the hand knob is, we know where the hand region is, but we don't know exactly where it's going to be maximal to make this twitch. Okay? So we use TMS, and then we go and we stimulate that whole area, and we measure the response. When we find the area that has the maximal response, we say that's our target. Okay? We do this for every single subject. Okay? So here's an example of two subjects. In this subject, you see this little orange spot right here? That's the maximal spot that produces the biggest thumb response. Okay? In this subject, you see, this is the hand area. Look how different it is for this subject. In this subject, this is the spot. Okay? Even though it's the hand area, nobody's brain is the same, so you wouldn't expect anything to look the same. Okay? So in this subject, this area is equivalent to this area now in our head model. You see this little arrow that comes out? Okay? If we turn on this arrow, if we turn on, in our model, if we say current flows from here out into the scalp, it would be maximally positive here and maximally negative here. And you can see these 8 electrodes here. 1, 2, 3, 4, 5, 6, 7, 8. And then 8 electrodes here. Reciprocity tells us if we use these 8 electrodes and these 8 electrodes and pass current through, we're going to have the best chance of stimulating that area. Okay? In this subject, look at this pattern. This is the hot spot. It's these 8 electrodes and these 8 electrodes. Very different. Okay? What people do normally is they do this, and that's it for everybody. In these two subjects, that is not even close to the best way to stimulate that area. So we do this for 12 subjects. Okay? And here are the results. And so we have an anodal condition, a cathodal condition, and a placebo. Again, the cathodal is when this is positive. The anodal is when this is the anodal is when this is positive. The cathodal is when this is negative. Okay, and actually we don't define it that way. Okay, we define it relative to the cortical surface, because remember, it's not this up here that matters. It's where the current flows relative to the cortex. So we always define positive and negative relative to that. Okay, but remember, we said we don't think that's the important parameter anyway. But we did it. Okay. And then we have a placebo condition. That's where we stimulate for a very brief amount of time, maybe 30 seconds only. So there's only 15 pulses. And remember, people can't tell that current is going through because they have lidocaine, so it's numb in all 3 conditions. So, but still, subjects can, a good portion of our subjects can tell it's a placebo because of this. When you pass current through, sometimes current, depending on the pattern, can cause flashes in your visual field. It's called phosphenes. And so that's unavoidable. And so sometimes they know it's a sham condition because they don't see those phosphenes. But in about 30% of the subjects, they can't tell because they don't experience the phosphene at all. Okay? So here is, so this is MAP amplitude post reference to a baseline, and 1 is the baseline, okay? And anything below 1 is considered a decrease, okay? And so ignore this for the moment. They seem to all start off a little bit negative compared to the baseline, or reduced. But you can see the placebo is pretty consistent, okay? And I'll explain this in a minute. But you can see that according to our prediction, it doesn't matter the direction of current. We expected a decrease throughout. And indeed, that's what we find, okay? But the big thing is, the cathodal seems to be a little bit more effective, okay? And here is the first 30 minutes after, so this is, immediately after to 90 minutes after. We see that compared to the placebo, so this is important, you always have to have a placebo, even though, these are negative relative to the baseline, we really want to know, is it different from placebo? We don't want to know if it's different from the baseline. We want to know is, if people think that they're getting something, does it differ from that? In the first 30 minutes, this is different. This is not different. Even though it's more negative, it's not significantly different. After 60 to 90 minutes, it's still significantly different. So this is long-lasting, okay? So, one of the interesting thing is, why do we get this difference? Why is there this asymmetry? We predicted that they should both be inhibitory, and that's what we see. But this is just more effective, for whatever reason. So why is that? Well, again, when you look into the literature, you always find something interesting. People don't report it, or they report it, but they don't make a big deal out of it, or they don't emphasize it, because it doesn't match up with the average response. Okay? And you'll see this in ERP research too, if you look at individual subjects. They don't always look like the average or the grand average. But there have been at least 3, I know of 4 now, that have shown that in rabbits particularly, when they record at the brain surface as well, that for whatever reason, again, their cathodal stimulation seems to be better, more effective. That's what we observe as well. Our explanation for why cathodal seems to be more effective goes back to this idea of the cellular layers. If you think about the model of, I'm going to skip back really quick to here. Remember, this is, so now we're talking about layer 1 up here, right? Layer 1. And if we pass cathodal current through, what's happening at layer 1? Layer 1 becomes depolarized, right? Everybody follow so far? Okay? So if this is the motor cortex, and this is layer 1, and this is layer 6, we pass cathodal current, meaning positive current goes from the bottom to the top. What happens? The top becomes depolarized, okay? And what is the significance of the top layers? The top layers is where all of the other inputs come in, right? And when you are depolarized, you're affecting changes at that top layer, okay? And it's the changes, sorry, let me correct myself. If you pass current from the bottom to the top, which is current positive to negative, the top, hyperpolarized. The top hyperpolarized. And all the inputs that go into the top layer become depotentiated. Okay? That's our explanation for the differential of why, even with the pulse protocol, you have more a more effective response, because now you're affecting the input layers. Okay, that's our described mechanism. Okay, so let me just. Okay. All right. And people have found this too for TMS. But again, people haven't made such a big deal of it. But if you look, it's there. I won't go into that too much. So this goes against some of the common belief, of anodal is always positive, cathodal is always inhibitory, or anode is always excitatory. And that's really the somatic doctrine, okay? The somatic doctrine really says that the net effect of TDCS depends on what the polarity is, whether it's hyperpolarized or depolarized at the body of the cell. Okay, that's that model I showed you at first. Anodal, excitatory, cathodal, inhibitory. It's because when you measure it across the cell, that's consistent with what happens at the cell body. Okay, but we know that the terminals must be important. It's the terminals that take all of the inputs from other areas, okay, and that eventually get summated at the cell body. We think it's the terminals that are really important, okay? Because really, again, back to this model, it's the terminals that have a lot of calcium receptors, okay? And so what you're changing is the calcium influx at the terminals where they're densest. Okay. So how consistent are these responses? So so I showed you the average, or the grand average response. Our hypothesis is it should be a lot more consistent, right? So here are the participants, okay? 12 of them, anodal, cathodal, placebo, and this is again change in baseline. Just look at the cathodal, and remember baseline is here, okay? Most of our subjects in the cathodal is below baseline. Again, and for the anodal, we have a good percentage that are below here. This here, this outlier here, explains this graph. Explains that right there. If we remove that, this goes down, okay? But we don't remove it. People like to remove outliers. Sometimes it's good for statistics, but it gives a distorted picture. So we just keep it in there. But you just so you know that they're always outliers. It's important to understand them, or not. But at least you have to show that, okay? So this is the distribution. For the most part, it's very consistent with our proposal. Of course, you have these three. But let's compare statistically with the expected. Okay. So here, what we want to know is when both are cathodas inhibitory. Okay. So here, according to the expected, this is cathodal inhibitory and also cathodal inhibitory. Okay. You expect a 41%. Okay. For us, this is our distribution, about 83%. Okay, so that's significantly different than, that's twice as much. Okay. Now let's talk about when anodal is inhibitory. Okay, that's about 26%. What we see is it's about 67. Okay, close to 3 times. So that's also significant. And then we want to ask how much current, total charge, or sorry, how much total charge are we putting in compared to previous studies? So we can do total charge here. So it's essentially how much current over the 100 millisecond pulses that we do for 17 minutes. And we just sum that up. And the unit is millicoulombs. It's about 60 in our current study. In previous study where they used TDCS, about 60 millicoulomb, they get no change whatsoever. Nothing happens. You have to go up to about 300 to see some effects. Okay? So with the pulse, because it's more physiologically plausible, it's more realistic in terms of how cells respond, you should use you should need less energy, and that's essentially what we see. Yes.
So have you tried instead of using the frequency of 0.5 hertz, have you tried more time through whole stimulation period to compare the previous study? I mean, the numbers are different, right? But
yeah.
You change it 2 things. First, that you pinpoint that anatomic area first.
Yeah, no.
And also you change it.
That's right.
parameter.
That's right. Totally right. And this one may be an indirect, but answer to that. But this is, we know this is in our study, we said we have a confound. We can't separate those 2 very clearly, and we need to do that. Is it because of the pulse, or is it because of better head model? We don't know yet. But here is our present study compared to other pulse studies. Okay? And you can see here, our pulse is still very short compared to others. Okay? But that's not a direct answer to your question, because you still have to run that. We haven't done it. That's something we'd like to do next, is separate that out. Yeah. Okay? So here's the study summary. We can get reliable long-term depression, and it can be induced with either anode or cathode. The effects are weaker for anodal stimulation, but it's still very consistent, or relatively more consistent compared to previous studies. And we didn't need that much energy. And it's a promising protocol for applications such as seizure suppression that require predictable suppression of corticoexcitability. And indeed, that is something we are doing right now at 2 sites, at Harborview Hospital in Seattle, Washington, and at Huashan Hospital in Shanghai. And it seems to be somewhat effective when we count spike rates. You know, these discharges that people, epileptics have. We can compare their discharge rates before treatment and after treatment, and there seems to be an effect. But so far we only have five patients, so we can't say much. Okay. So that's essentially an introduction to GTEN. So I'll stop now and take questions. More questions.
Okay. Is it possible to stimulate subcortical area using your GTEN?
Great question. The answer is we can go deep, you know, So we can hit the medial temporal areas, cortical areas, but for subcortical areas, we can still hit it. But the problem is this: that their net effect, for the same reason that we can't measure EEG from deep structures, is the same reason why we can't modulate them, because they're all randomly oriented. You know, so they have to be oriented like this for the current to have a net effect that influences the polarization and depolarization across the axis. For subcortical structures, you know, they're all randomly oriented. And this is why it's so important for us to have the good models, even at the cortical level, because it's really, you know, when current flows, it takes all directions. So if this is the cell, it goes this way, and you pass current through, some will go like this, and some will go like this. It's only this that really matters. So for us, in our model, we always model the current that goes this way. So we pick those electrodes that are optimal this way. And that's really important. And that's called radial current. So for us, we do that. Now, if you go to the subcortical levels, you can't do that because they're all randomly. So we don't think it's effective for subcortical structures.